l'université avant d'aller faire son master qui s'appelle en architecture navale. Et donc, je suis mené à faire pas mal de travaux autour de la bio-inspiration, beaucoup de choses qui baignent dans l'eau. Donc, c'est un peu finalement, c'est la suite de ce qui a été présenté ce matin. Après, des systèmes de capteurs, des systèmes un peu de stabilité, structure, écoulement. Bah là, il va présenter finalement quelques applications qui peuvent aller dedans. Et donc maintenant, donc, il est de retour en Chine, à l'université de Westlake à Hangzhou. Et donc là, il a sa propre équipe pour labo. Il va présenter un peu ce qu'il fait. Je lui ai demandé de ne pas parler trop vite pour espérer que le maximum d'entre vous puissent suivre. Mais vous allez voir, s'il y a beaucoup d'animation, ça va être, je pense que ça va être très bien. So Dixia, I was just saying, I mean, beautiful things about you. So, so now the floor is yours, and I thought that'd be amazing.
Oh, thank you. Thank you very much, Guan. Je parle un peu français, so I don't know what Guan really says. Like, probably she's just speaking very bad of me. So, but anyway, it's my great honor to be here. Like, I'm so excited. And as the title says, like learning from animal. Actually, it's not about this. So today I'm going to basically telling some story from a big kid playing big toys. The first big toy that like Guan and me like play is like here in 2019 in the science robotics. We on this pink couch which I hate so much, but Guan really likes. So that's why we are enemy. It was like so can we build a robotics can replace us? So doing experiment the way like we just like playing a video game while the robotics doing the experiment for ourselves, and it works. So it ended up in a science subjournal. But today, as a big kid, so I need a playground. So what is my playground right now? My playground is a new campus called Westlake University, and it's a very also very small university, just like a ENS, like a Rennes. So that's my playground. So what is exactly toy that I'm playing? So I'm playing like an underwater vehicle. So this is traditional underwater vehicle. Being 10, 20 years. It's super expensive, can go to like $1 billion each, and they're very, very compact, very consuming, very, very stupid. So wasn't it a good idea? Dolphin says, no, it's not. But also, can we also do like a robotic, just like this cute animals? So maneuverable, so cute, at the same time to help us to explore the ocean. So what should we do? So I think I draw this my friend Zhongqiang draw this picture. So say if we want to do this new generation robotics, maybe we need to understand nature better. And also unlike propeller, which one of the gentlemen just had foil, which man-made really great a structure. There's no a rotation motion in large animals. There's always an oscillator motion. Can we design new devices? And sometimes the fluid mechanics the gentleman just said the unsteadiness in this oscillator motion even worse how we control and better sensing that. So allow me to tell 5 stories very quickly. I guarantee there's no math inside, just story. So let's first do a comparison between fish and ships. Whether a ship is a good idea or whether fish is a good idea, and then we go to something can we play some Lego pieces building a robotics? And then let's talk about some deep reinforcement learning, and the fourth one is actually a student co-supervising between me and Guan and help Alex is here. So did a very interesting job jumping bird on the water, and then I'll tell you the recent success I have in just 2 weeks ago. So to begin with, the fish with flat. So assuming this is a submarine, you will see this beautiful vortex shading in the water tunnel, towing tank. That's one common vortex tree. You see this very coherent, but that's bad. That's a drag because that will be pressure drag behind, right? So so in 1936, there's a very famous scientist called James Gary. He said the fish swimming like supposed to have an energy balance. The thrust, the drag should be balanced. But in reality, no. He calculated, did a little bit to find like the left-hand side is 7 times larger than the right-hand side. Why is that? So allow me to show a video, which is from George Lauder's group, from Harvard. And the fish, the water turtle, right is right come to left. And the fish is just a rainbow trout is swimming there. You say, oh, what's so boring video? What's the meaning of a fish? Then I will tell you that this fish is a dead animal. It's a dead, So then you say, you must be cheating, because how come a dead fish not being washed away by the water and even going forward? Yes, we cheat. How do we cheat? So there's shadow region, you see there. There's a cylinder. That behind that, there will be vortex shading behind that. And because the fish flexes the body, it can synchronize the vortex, gliding through this vortex and moving forward. So basically, that's evidence showing that the fish doesn't need energy to some degree, can moving forward. So, smart choice. Then what's next? We all know underwater, they're rotating large distance. But look at this live fish. This is actually, again, really live fish are collaborating, famous, they start to curve its body and jump. They measure that underwater, they can achieve 100 meters second per square, so 10 gravity in terms of acceleration in the water. How do they do that? So let me first put a ship model which towing sideways. You see in the bottom there's a coherent vortex shading. We call it helical vortex shading. That's a bad for drag force. That's actually instability for water. So and we see let's go here. So let's do a PIV, and you see when they curve its body, it suddenly flips its tail. It's like a big body of water coming out. What is going on? So basically, what's going on is the fish intentionally curve its body in a C shape, so creating a pair of red and blue positive negative vortex, and use the tail to swipe these vortex like a rocket, creating a jet sideways. So with this jet, you have a jet creating huge lateral force. So, long story short, for vortex, beautiful. For ship, bad. Vortex, for fish, good. That's the only story I want to tell for the first story. So, now we know that the fish, with a flexible body, all the things, can really create a very efficient and maneuverable creature. So can we build these things? It's difficult because it's flexible underwater, all the things. So, and also if you want to build big stuff, it's difficult. So, and matter of fact, we say oh, we want to one of my dreams is let's build a ship myself, but if a 3D printer ship, let's say 10-meter ship, you get a 20-meter 3D printer. So why not let's be kids playing Lego pieces and building things together. So these are the these are 7.5 centimeter big. So each plate looks weird at the beginning, but if you put these things in a box, then put a box into a cluster, it become bigger and bigger, then they start emerging some nice property. So for example, this one is rigid, this one with squeeze that it's flexible, and this squeeze that it can shrink oxidic, and this one can rotate. So that's become basic element, bits, and we can build big stuff from there. So what did we do? So I'll just show this rigid thing. So we actually sent 25,000 pieces to Kyoto University. Over 48 hours, we didn't sleep. Remotely in COVID, we built a vehicle can go onto the can drive. But the one thing really bad that day we didn't expect, it's raining, so it's actually collapsed. But the collapsing, it didn't break. So that's a very nice thing. 48 hours, 2 days. And also, we say, oh, can we do a fish or something? So this is Robert Turno. That's the supervisor for both me and Gilbang, in MIT. And that cost 3 years, 3,000 components to build. This one is exhibited in Great Britain Museum by my professor Michael Chenfulo. It's solved the Gary paradox in old time, but it's really time consuming. Can we do that in 1 week? Yes, we did. Using a rigid and flexible, let's say oh, can we build like a spine? The spine is like flexible in one direction and rigid in the other direction. So, and these just pieces, and of course not as fancy as rubber turtle, but we built like 1.5 meter snake in 1 week. And we test that, and start to like swimming really nice. And it's actually started generating thrust force because don't forget that's the vortex is like going on. So again, the toy happens, but I do want to point out one thing really quick is like, so you see the this like sketch, that's our prediction. And you see that like the actual thing when it's moving, it's actually not well follow the trajectory. Unlike a propeller is controlled like in angle or the things. This is like because half rigid, half flexible. You need to consider about how the dynamics, how the kinematics of the fluid, how the structure, all things together. So, still not good enough. So, how can we do that? The traditional control, traditional understanding will be difficult. Oh, that's just showing like because like when you're like not moving, it's like the wake is like this. Now you start have like this vortex have a jet, so creating some thrust force. So we start having some like toolkit. Although there's like a multiple toolkit in the my arsenal to like build different like robotics. But say like you start have these toolkit, how you control that. So I want to show you some like promising results that recently my student just did like in a very good way. So let's start with another cute animal, puffy. So another like direction in my lab we want to do is like building robotic can both fly and swim. Why is that? You can scan a large surface, then dive, then coming out, like you have multiple purpose. So of course like it's difficult for like for traditional one because you can see like on the air you need a lift force, in the water you need a thrust force because Archimedes already take care of like the lift force. At the same time, if you see propellers or like a wind turbine, you see the blade is completely different because they operate in different region. So nature already provides some idea, say, oh, there's a puffin can both fly. They not fly as good as eagle, they not swim as good as fish, but both important, they can both fly and swim. So what's the secret behind that? So one of the secret is that when they flapping its wing, so they just apart from starts like a shrink a little bit, like a changing the surface, also they change the trajectory of the wing. So for example, they did this. So if it's like I'm not going to go deep into like a flapping foil theory, but let's say like if you're flapping its wing not in like symmetry perspective, it's like non-symmetry. And like if you're flapping its rigid wing like in this trajectory, what's the result come out? Let's see some PIV result. And you see that when it's flapping, it's like have a huge leading edge vortex and trailing edge vortex, like being washed down the water. And like if you really look into that, basically these leading edge and like trailing edge vortex creating huge thrust, huge like jet, which creating like this unsteady lifting force, not a steady lifting force. While if you push like the bottom was like a turtle did, you'll see like they will push out like a vortex just like a rocket, like right huge rocket like jet, phew, and creating jet, and that's actually creating like thrust force. And you say, oh my God, that's great. We finished our story. Like you can using this propeller to like a fish and so. No, it's difficult. Why is difficult? Let me just show you these two. What these two is, so you see the trajectory almost exactly the same in quotation, and this arrow is the instantaneous force. You see the force is completely different. The top force, you can see even the drag force. If you focus on the like, here, you see that like the top and one, the angle, instantaneous angle of attack is slightly different. It's these slightly angle difference will creating like a huge difference in the force profile because vortex is very nice. It helps us to like creating these force or the thing. But the problem is it's nonlinear, time variant, large parametric space. The traditional like control theory, like if you go to a control series, like, oh, I want to control a nonlinear time variant system and with a large parametric space. Like, come on, man, like forget about it. So what's the solution? We start doing something nice. Like look at like even worse. Like so, we start putting some reinforcement in. Like a reinforcement in. Like if you don't know, it's just like give a candy to a kid. give it more candy, it start like explore a very nice way. So you see that without any knowledge, starting from like this sinusoidal motion, very periodical, like you can parameterize it, going to very weird motion, like still periodical, but actually getting much better like a thrust force. And I just want to show some like very nice result like in this one. So this is like a thrust coefficient and energy, this cut off, that's like an energy efficient coefficient. All the blue dot is like the traditional using parametric like sinusoidal motion. We did like 20,000 cases, like a brute force, get to like this pitot front. And you see the red dot is trained by like the intelligence. It can increase by 15 to like 25% of like a performance because it started like using like a non-parametric like a motion. The reason why it works is like even though it just seems changing slightly a little bit, but it's changing the thing like a relative motion between vortex and, for example, there's a vortex shading here. Instead of like moving slowly, they quickly like catch that vortex. By changing that phase, we're changing completely about like the hydrodynamic performance. Okay, seem we have some solution. So can we put it into like a practice a little bit? Oh, another story. So that's actually like another interesting like story that like we did. So like I just don't want to like too over the time. So like this is actually like we have this story with like Alex is a student actually from here, right? Yeah, Alex is a student from here like before. So and also another student working with me like we actually like have like these two students like have like fun like watching YouTube video. I assume you guys all like to watching YouTube. They actually find a bird called a white-faced stone petrel, mesmerizing, can actually jumping on the water, like cute animals, all the things. So they say like told me and Guillaume, we want to build this robotics. We want to build a world first robot can jumping on the water. Very ambitious. Great. 5 years later, I'll see you. So of course, like it's not that easy like story, but we should get started. So let me just like want to like pay my tribute to the nature that like you see like have you think about how actually birds start flying from water? They actually have using a lot of their wing, but also their feet. On top of that, there's something called a grebe that like later like let's restart the video and you will see that this grebe can actually on the middle left, you will see that two pairs, that male and female, start getting up and like running on the water, and they're big bird like this big. So like so it's not easy like and of course there's a very famous like working before in 1999 and 2004 by George Lauder and like his supervisor is basket lizard can walking on the water. So we say like okay, there is this like a stone patrol by the way like I'm a Chinese. My dream child Chinese to know kung fu, right? I mean it's everybody's dream like like if I can like walking on the water like these like movie, oh my god, that would be cool, right? Considering my body shape right now, probably not. But anyway, so like with that being said, like so how we do that? So we see a lot of like videos. So we're actually working with some biologists like in Washington, and we actually get a piece of full like stone patrol body from the like museum. We actually really carefully measure all the like body shape, body types, all the things. We start like simplify that. That's what our engineering work. Biology is complicated, but we can start finding some principle from what we learned, and we simplify it to a 9 degree of freedom model, and say can itself, and of course we also put some like force model, like a wing, we have like lift force, like and we have like a thrust force, we have like jumping force, like impulse force on the like a touching of the water, something like a very quick like reduce all the model, not like a numerical, not a CFD, that's impossible at this moment. So say, oh, we have like this model. We don't know how to like play its body, so I want it like but I know that I want this body to jumping, pew pew pew. I want this body to anchor and location with the wind blowing. Can the like smart of like AI help me to do that? We designed a neural network. We designed we designed like a reinforcement like learning framework. We put that into the piece, and let's see what's the result. So let's first focus on the top half. So that's when we give like results. Say you keep like going to one distance like to another distance as quick as possible with touching the water. That's the objective. So of course we build some like a reward. That's the reward is like, by the way, talking about AI, I don't think we're losing job because still this reward is built by us, but it's a complicated like large parameters go to like ChatGPT. You see that like at the beginning like it's sync, don't know, early bird, just like us when we were a baby, crow, boom, falling down. Now we actually see later with the time passing by, it's able to emerging this like jumping behavior. Very nice. And top of that, like sometimes we actually like put like some other like reward. Started feeling like, oh, this like being a huge wing blowing and being blown away. But then like actually start anchoring to one point at a wing. And actually we see in nature they can able to do that because they're able to open their wing to like balance the wing like speed, so creating lift force. But the wing of course have some drag, but the feet like in the water trying to trying to do something to balance that like drag coming from the wing. So this is nice. So on top of that, like we're working with some biologists, we can actually very accurately like reproduce what is the force, at least in hypothesis. What is the force on the feet, on the wing? So for example, like you may think, oh, if I want to jump, the feet must provide a lot of force. No. The feet only provides impulse force, but that's the magnitude is large, but the duration is small. So that's not considered very much in terms of like creating like a balanced like the weight. So in the way that's a pretty bad news for me. Means like I need a big wing to actually do that. Like even I have feet. But that's actually very nice information for like biologists, help them to understanding maybe what nature really does. But also like that's like the starting point for my PhD gonna starting in this September is like he draw this like, oh, maybe in 4 years, hopefully in 4 years I coming back, I can show you, oh, here's my bird robotics and there's the water, go, and pew, 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 jumping, right? So another toy. So then let's go to the final toy that like, I mentioned like I want to go to the ocean, I want to like building like that nodding on like a shaking head dolphin, like what I did in last 1 year after I coming back from like the States and Canada to China. So we say, you know what? I want my big toy. Big toy that like not like a traditional vehicle, because traditional vehicle is bulky, maneuverable is bad. I want it to be silent, to be like elegant, to be less environmental intrusive, like a stingray, like a manta ray. So we start building this robotic, and you can see me and the size of that. And that's the test of like this. And we of course test like my students, my colleague, of the team. Like we go to like test like first in the shallow water. It works. It's able to swim. I'm not going to go too deep in terms of like technology perspective, but I just want to give you an idea. This one going to 2,000 meters, how difficult it is. 2,000 meters, 200 atmospherical like pressure, equivalent atmospheric pressure, 20 megapascal, so even the traditional like buoyancy material going there will be squeezed to pieces. You will lose buoyancy, even the traditional buoyancy. And then you also have like a water tide. You have like limited energy perspective. How do you manage it like a power? How do you and don't forget, I want this to swim by itself without any intervention. So that's 2,000 meters. Go out. The communication is really difficult in water. Like you can only using acoustic, like sometimes using light, but like not in 2,000 meters. How it's going away and coming back from ocean from 2,000 meters. So there's some people say it's more easy to go to space than go to deep ocean. So we try to address this. I just want to use one example. Like, even a small point of like, an outlet, like, because this outlet, if we want to connect underwater, there's like 2,000 meter, like, even the Earth is 11,000 meter, like depth of Mariana Trench. How you actually design the whole system is like difficult. For example, these outlets, like, if we want to buy from America, each one costs roughly 150 1,000 euro, like for each, just like this big. So I don't have this money, so how about we build that? Yes, we can build that, like not as fancy as them, but like with the fundamental knowledge of engineering, we did that. That's also maybe the reason why Gilbert asked whether it can go to deep ocean for high pressure, like all the thing. So we did that. So, and is it working? Yeah. So you can see it's like in shallow water. We have some people like start walking. You can see like the movement of human being, like the speed. Not bad. But then like that's not like oh, I apologize for Chinese though. So in April 23rd, so a couple weeks ago, 2 weeks ago-ish, we go there. We reach 2,053 meters in China's Southern Sea with like the new boat, and you see the retrieve like by itself. How we did that? We actually didn't go swim by itself down there. We have like a system like connector go to 2,000 meters, release that, so swim by itself like away, like 3 kilometers away. Once the swim finish, it's actually slowly swimming up by itself, trying to like come back to daddy. So what you did? So you may say like deep ocean, why we care? So this is what we filmed in deep ocean. So it is like desert, but suddenly you have something like surprise. You see there's like look like garbage there, but that's an animal that actually can jump a little bit. So I don't know whether you guys have seen it. Let me replay the video. You see, it's moved a little bit. So I don't know what that is. So like our like a friend Guan and like our colleague from like Cambridge, we gathered together. We say maybe that's a deep water frog. So because we are eating very nice frog leg here, like yesterday. So after a couple of drinks, we're like, oh, maybe that's a deep water frog. And James like after a couple of drinks, Dixia, just get that for me. I mean, I want that leg. I don't want like the leg from. Anyway, I don't know where it is. So and also I also want to share my pure moment when I see from the deep water it emerge, like the moment when it emerged. Later I will play the video. You will see like something going on there, very small. We are on the ship. So you see the white thing? That's the moment when it's coming back from 2,000 meters. Because like that time like we have like acoustic tag there, so the ship knows where they are, but my toy does not know where we are. So everything automatic coming back from 2,000 meters after like 3 kilometers away. So that's a moment of like say engineering works. So let's go back to this picture. I'm still like playing toys like long time far apart. My dream is shooting my body to like Saturn, Mercury, go deep to their water there, like if possible. So, where we are. So what do we do next? So we actually like two years ago, me and Guan almost meet every week, like apart from trash talking each other. So like is that what should we do? We say, oh, we want to be like a fish. Oh. The fish, like we know like some fish like dynamics, but we don't know what fish really thinks. Can we say like from being Nemo, from being Gimo or Gummo, whatever? So, but how do we do that? So we actually apply for Human Frontier. We're very successful from like maybe 700 people coming out as like couple one. We win that. With like colleague in Cambridge in ENS, we say like, can we say like we're working with live fish using numerical with Mécatroniqes. We're starting actually like recreating what really like fish thinks. It's like a Nemo fish, like not a Nemo fish, it's a private joke. Anyway, with that, I want to say thank you very much, and that cannot happen without a group that I built in last 1 year in China, and with all the kids, basically we are big kids playing big toys. Thank you very much. Oh, right, merci. So the only French I know, merci, and je parle un peu français, so. Ah bon, 谢谢, yeah.
I know too well. Thank you very much, Dixia. So there may be questions. Il peut y avoir des questions que je peux même traduire si vous voulez m'entendre parler en français. Just saying that we can translate it.
Yeah, sure. Or if you want to speak asking Chinese, that's even better. So.
Hello, thank you very much for your presentation.
It's working.
Okay. Do you think in order to build a deep water engine, we should go fishing and learning from those fish that are deep underground, deep water, and build robots in scaling from them?
If I can understand your question, should we learning from fish to build robotics compared to the traditional ship? I want to say that the current ship works. It's not like we are kill the shipyard business. No, we're not. The current ship works, transporting large, a mass of a product that works. It's just in some activity, it may be not the best option. For example, now there are being people say we want to explore the deep water to actually get the mineral from the deep water. The technology work already been existing, but people really say no. Why? But think about traditional mining industry. It create a huge mass afterwards. Deep water, thousands, 100,000, million years have not changed. If you have your current a moving vehicle to do that, it's gonna destroy the whole nature by all means. And you see that the robotic very gently doesn't seem arouse too many surroundings. That's maybe an option to search and grab some mineral off the ground. So the traditional vehicle didn't work too well. The second option, second example, for example, there's in the deep water cave. Even their cave, they're inside the deep water. There's very interesting system there. Traditional vehicle cannot navigate into that because their maneuverability is so bad compared to the fish. But fish can very easily go in there to do their business all the things. Can we build a robotics or vehicle that as smart, not smart, as maneuverable, as agile as the fish to go to these places that a traditional vehicle cannot go? So there's so many examples I can give, but in short, there's I think with the traditional vehicle, traditional ships, they're doing a very good job. But there's something we want to do even better. So these two things can be a two legs as a human being. One is ship, one is underwater bio-inspired vehicle to do a better job in exploring and exploiting the ocean. That's my answer.
Okay. Thank you.
It was a very inspiring lecture. Thank you. Actually, one question. So the research that you do, so it's part watching YouTube videos. A part is doing simulations and setting up a control network, and then finally is realizing the thing that you design. So what kind of percentages? How much time do the students spend watching YouTube? How doing console, and how much time do they spend realizing the device?
Yeah, well, that's a very good question.
There's a fourth thing, of course, you should communicate, so there should be WeChat or... So
I think like, let's start with like communication. A lot of time, these projects, I'm doing my own project. I'm doing my big ship. I'm actually a theoretist. So I like to derive naval statistical equation. I like to derive vertical flow control theory, all the things. But also I like to build robotics from a very small young age. So a lot of these projects actually is students coming to me, say, you know what, Dixia, I want to do this. Give me the money. Give me the time. I was like, well, I'll try to find you money. I don't think I'll have enough time, but I can find the correct people. Like, for example, like, we actually, like, these, like, that's a communication. In terms of, like, in terms of, like, modeling, like, in terms of, like, abstract, so coming from a complex system to going to, like, engineering problem and the modeling to understanding control sensing, my philosophy is, like, there's a very wise, like, Chinese man says, no matter it's a black cat or white cat, if it's if able to catching mice or rat, it's a good cat. So what I'm trying to say is that, so I think in reality, that if one system work, sometimes it's not like have one subject going to extreme like well, we need a theory going on. That's what I'm doing like in my own research time. There's also time like I need to find really a group of people in different expertise, putting knowledge and putting like a technique or sometimes like new solution may emerge from trash talking with each other. I will give you an example, like really exciting example with the beers, with what's the like dessert I eat yesterday. The dessert I eat yesterday. Quinnaman. With like the oh my god. So and also backseat of the taxi. So yesterday like Gilbong and me and also our British colleague comes and say, oh, we show it works, and they say, Dixia, can you measure like the metabolism of like a fish in the deep water? I was like, yeah, nobody have ever done this because if you catch like some creature from deep water to go, everything dies. So it's not that difficult from an engineering perspective, like to capture like things like to attract things and do this. It's literally on the back seat. We start like talking about like possibilities, like all these things. So for me, like measuring the metabolism, these things like so far up in the like in the future, like also. Apparently that's an existing and like technology for the biology group. So I'm going out of picture at this moment. To summarize, one word: interdisciplinary, finding the right person. Like here, like in Ian's Rennes. Yeah, that's my not very answered question to you.
Thank you. I go back to my question. So what is so actually
the time.
About how much should there be like theoretical modeling,
Yep.
And how much should there be like actually making the thing?
It should be more like dynamic. So I cannot give a like actual answer because like it's also varying time all the things. So so one thing I'm very happy with all the students right now, they are become very good PI in themselves, like principal investigators. So they actually really know how to. This is the part like in the last 1 year, I really trying to help the student how to manage like the project themselves, all the things. So that's where they are. At least like from the like this picture, you see they're happy, they're smiling. So that's a good thing. So like. Yeah, half of the team are engineers. So yeah. So they, yeah. So they're half engineer, half like students. So some theory and like this like really works very well. So. Yeah.
Thank you for your presentation. I assume that the issue of the quest to the depth of the ocean is about the pressure. So do you think that with our technology, our actual technology, we can reach a depth like more than 2,000 meters?
Yeah. Yeah, there are people like going to 11,000 already. So there's like a generation 1, generation 2, generation 3 vehicles. Like, we are in the phase of like, say, at least I'm self-called generation 3 vehicles. The first generation is just like there's no power, just go down. The second generation, like the one I showed, have a little bit of power with a cable. So the deep water pressure is one thing. I think like a material, like a mechanical design is getting much better. Another problem is like the communication. The communication is really bad. And third problem is the power. Like how do you get power? Unlike fish can eat fish, we don't have like this opportunity to how you manage power. And of course, another thing, if we want to build these very interesting robotics, so it's not just like say we can like say have a propeller to just go like left and right or thing. You need to like really how to control the body, like so the fluid mechanics is like become more and more important, I can say. So like so for structure, no problem. So there is a problem in terms of structure is that yeah you can say I'm using titanium, right, and it's this thick of wall. You can go there. But that's too heavy. How you design things much lighter because there are fish under like 11,000 in Mariana Trench. They don't have like the bone this thick. So how we learning from nature, from structure, getting better and better. That's another like challenge question we can go for. Like that's answer. Did that answer your question? Perfect. So.
Merci, on se retrouve à 13h40.